Silicon electrons collide every 10 nanometers due to lattice vibrations, which limits their transit speed. Graphene allows electrons to move unimpeded across the entire transistor channel. This phenomenon is known as ballistic transport. In standard semiconductors, velocity saturation occurs when electrons lose energy to the crystal lattice. This thermal dissipation creates a speed ceiling for modern processors. Graphene bypasses this limit through its unique lattice structure. Mean free path represents the average distance a charge carrier travels before changing its momentum. In silicon, this distance is usually under 40 nanometers. Graphene routinely exceeds 1 micrometer at room temperature. Ballistic transport occurs when the device channel length is significantly smaller than the mean free path. Under these conditions, electrons behave more like waves than particles, avoiding traditional resistive heating and scattering. Graphene consists of a single layer of carbon atoms arranged in a hexagonal honeycomb structure. Every carbon atom forms 3 strong sigma bonds with its neighbors, leaving 1 electron in a pi orbital. These pi electrons are delocalized across the entire sheet, creating a highly conductive 2-dimensional electron gas. The geometry of the lattice determines how these electrons move and interact with external electric fields. The electronic band structure of graphene is unique because the conduction and valence bands meet at single points. These are known as Dirac points, located at the corners of the first Brillouin zone.
Near these points, the energy-momentum relationship is linear rather than quadratic. This mirrors the physics of massless particles, causing electrons to behave like photons with a fixed effective speed. These charge carriers are described as massless Dirac fermions. Because they have no effective mass, they require very little energy to accelerate, leading to extremely high intrinsic carrier mobility. Mobility in graphene can exceed 200,000 square centimeters per volt second at room temperature. This is over 100 times higher than the mobility found in high-quality silicon wafers. High mobility translates directly to high switching speeds. As electrons move faster through the channel, the time required to change the state of the transistor decreases toward the picosecond range. A picosecond transit time corresponds to a switching frequency of 1 terahertz. Achieving this in silicon requires extreme scaling that leads to prohibitive leakage current and massive heat generation. Traditional transistors rely on drift diffusion, where electrons bounce through the material. In ballistic graphene transistors, the velocity is determined by the Fermi velocity, which is roughly 1 million meters per second. This Fermi velocity is constant, regardless of the applied electric field. This prevents the velocity saturation that plagues silicon, allowing graphene to maintain high speeds even at low operating voltages. The absence of scattering means that energy is not dissipated as heat within the channel. Instead, energy dissipation occurs primarily at the contacts, improving the overall power efficiency of the device.
To build a transistor, graphene is placed on a dielectric substrate. However, standard silicon dioxide contains trapped charges and surface phonons that scatter electrons, reducing graphene's natural performance. Hexagonal boron nitride is the ideal substrate because it is atomically flat and has a similar hexagonal structure. Using boron nitride preserves the high mobility and ballistic nature of the graphene layer. Encapsulating graphene between layers of boron nitride protects it from atmospheric contamination and impurities. This architecture allows for mean free paths that can reach several micrometers in length. In a field effect transistor, a gate electrode controls the carrier density in the channel. Applying a voltage shifts the Fermi level, moving the graphene from an insulating to a conductive state. One significant challenge is that graphene has no natural energy bandgap. This means the transistor cannot be completely turned off, leading to a low on-to-off current ratio. Without a bandgap, graphene transistors are better suited for high-speed analog applications rather than digital logic. They excel in low-noise amplifiers and high-frequency mixers. The lack of a gap is a result of the lattice symmetry. While opening a gap is possible through nanostructuring or chemical doping, it often degrades the carrier mobility significantly. Another quantum effect in graphene is Klein tunneling. Electrons can pass through potential barriers with 100% probability, making it difficult to confine carriers using traditional electrostatic gates.
Despite these challenges, the high transconductance of graphene makes it a prime candidate for radio frequency electronics. Transconductance measures how effectively the gate voltage controls the output current. Cutoff frequency is the point where the current gain of the transistor drops to unity. Graphene devices have already demonstrated cutoff frequencies exceeding 400 gigahertz in laboratory settings. The maximum frequency of oscillation is another critical metric. This value depends on the output resistance and parasitic capacitance, which researchers are actively working to minimize. Parasitic resistance at the metal-graphene interface remains a bottleneck. High contact resistance prevents the full realization of ballistic transport, as electrons struggle to enter the channel effectively. Innovative edge contact techniques are being developed to solve this. By contacting the one-dimensional edge of the graphene sheet, researchers can achieve much lower resistance and higher current injection. Scaling the gate length down to the sub-100 nanometer range pushes the device into the true ballistic regime. In this domain, the transit time is purely a function of distance and velocity. Unlike silicon, graphene does not suffer from short channel effects like drain-induced barrier lowering. The two-dimensional nature of the material ensures excellent electrostatic control, even at the nanoscale. Thermal management is another advantage. Graphene has the highest known thermal conductivity of any material, allowing it to spread heat away from the active junction much faster than silicon.
This high thermal conductivity reduces the risk of thermal runaway, enabling higher power densities in compact radio frequency circuits. It allows for more reliable performance at extreme frequencies. Terahertz waves occupy the spectrum between microwaves and infrared light. This region is currently difficult to access with solid-state electronics, a problem known as the terahertz gap. Ballistic graphene transistors could bridge this gap, enabling new technologies in ultra-high-speed wireless communication and secure imaging systems for medical or security applications. In the ballistic limit, the conductance of the graphene channel is quantized. This means the current flows in discrete steps related to the number of quantum modes available in the ribbon. Using the Landauer-Bodecker formula, we can calculate the maximum current a ballistic graphene nanoribbon can carry. This fundamental limit is dictated by quantum mechanics rather than material defects. Compared to carbon nanotubes, graphene is easier to integrate into large-scale manufacturing processes. Chemical vapor deposition allows for the growth of high-quality graphene on large copper foils. Transferring these large graphene sheets onto silicon wafers allows the industry to use existing semiconductor fabrication tools. This compatibility is vital for moving graphene from labs to commercial products. High-frequency graphene mixers are already being integrated into radar systems. Their high linearity and low noise floor provide a significant advantage over traditional gallium arsenide components.
Graphene can also be used in flexible electronics. Its mechanical strength and flexibility allow for high-performance terahertz devices to be printed on plastic or textile substrates. As we approach the fundamental limits of silicon, ballistic transport becomes a necessity rather than an option. Graphene offers a clear pathway to exceeding the 1 terahertz switching barrier. Research is now focusing on vertical graphene transistors. These structures use the thickness of a thin insulating layer to define the channel length, enabling even shorter transit distances. In these hot electron transistors, carriers are injected at high energies into a thin graphene base. This allows for ultra-fast transport across the base into a collector layer. The combination of graphene with other two-dimensional materials, like molybdenum disulfide, opens up the field of van der Waals heterostructures. These stacks can be engineered for specific electronic properties. For instance, combining graphene with a semiconductor that has a bandgap allows for the creation of high-speed tunneling transistors. These could theoretically switch faster than any current silicon device. Noise performance is another area where graphene shines. Because electrons do not scatter, there is less random fluctuations in the current, leading to ultra-low noise figures and amplifiers. This makes graphene ideal for deep space communications and sensitive radio telescopes. Detecting weak signals at terahertz frequencies requires the absolute minimum of internal device noise. The integration of graphene onto silicon carbide substrates is another promising route. This method produces high-quality graphene layers directly on an insulating substrate, simplifying the fabrication process. Epitaxial growth on silicon carbide yields graphene with very high structural integrity. This leads to longer mean free paths and more robust ballistic transport characteristics in the finished transistors. Current density in graphene can reach 1 million amperes per square centimeter. This is several orders of magnitude higher than the current carrying capacity of copper interconnects. This capability prevents electromigration, a common failure mode in traditional metal lines. Graphene can handle the high currents required for terahertz operation without degrading over time. The high-frequency limit of any transistor is also constrained by the gate resistance. Using graphene as the gate material itself can further reduce parasitic losses in the device. Terahertz spectroscopy using graphene transistors can identify chemical signatures of explosives or hazardous gases. The high sensitivity of graphene to its environment makes it an excellent sensor platform. By measuring the change in conductance as molecules adsorb onto the surface, graphene sensors can detect single molecules. This sensitivity combined with high speed allows for real-time monitoring. While digital computing remains dominated by silicon, the analog world is rapidly moving toward two-dimensional materials. Graphene is at the forefront of this shift into the terahertz regime.
The physics of ballistic transport in graphene is well understood. The remaining hurdles are primarily engineering challenges related to large-scale uniformity and contact optimization. Future wireless networks like 6G will require frequencies in the hundreds of gigahertz. Graphene transistors are one of the few technologies capable of meeting these bandwidth requirements efficiently. By eliminating internal electron collisions, we are moving from a regime of resistance to a regime of pure wave propagation. This transition marks a new era in microelectronics. Ballistic transport represents the ultimate speed limit for electronic charge carriers. With graphene, we have a material that naturally supports this mode of operation at room temperature. Reaching terahertz speeds will transform how we process information and interact with the electromagnetic spectrum. The journey from silicon drift to graphene ballistics is just beginning.